Hi everyone, I'm Matt. That is actually awesome. I like that. So today we're going to talk about rich comparison methods. To tell you a little bit about myself, I work for a company called Handshake. I'm the VP of Engineering there. I am very gracious to them for paying for me to be here today. So I'm quite generous of them. To give you a little bit of background on me, I went to college in 2002, and I got some great advice from my dad, which was that the internet is a fad, and computer programming is not going to go anywhere. So I listened to him, and I got a degree in something useful, philosophy. And so I think it's just kind of important to start off with a pretty basic concept in philosophy. So this is Aristotle's formulation of the law of non-contradiction. The simplest way to state it is that A is not A. This is more or less in Western logic like the base truth of all base truths. Like everything comes from this. It's a fundamental concept in identity. It's repeated throughout sort of the history of philosophy by Aristotle, Kant, a bunch of other people. So this talk is going to be very philosophy heavy, so I apologize in advance. So I wrote a little philosopher method. And so I'm going to load Aristotle, and I'm then going to compare Aristotle against Aristotle, and I get true. So when I compare Aristotle for non-equivalence against Aristotle, I should get false. I got true. So if you think about this for too long, you kind of end up in this I Heart Huckabee style existential crisis. So let's not do that. Let's take a look at the code. So I've been sort of obsessed with the Dunder comparison methods for a while, and it really sort of started with actually this problem. This is a real bug. Obviously the names have been changed to protect the innocent, but this was a real bug about 6 years ago that I discovered. When I jumped into the code, I looked at code that looked like this. This looks about right. So Dunder EQ is defined to check for whether or not the other comparison is the same instance as me, and if it has an ID. And if it is that, I do the equivalence comparison between self and other against the ID attribute. Otherwise, I return not implemented. A lot of you are going to say that's wrong. Returning it, not raising it. It's not wrong. We'll get to that in a second. So the problem here, actually, so I spent about 8 hours looking at that. And what I should have done is actually just gone with documentation immediately. So the documentation for the Dunder comparison methods actually sort of calls out the problem immediately. And the issue is that we sort of have this baked-in assumption where it's like, well, if something is equal to something, it must be not. It must the value for the not equals operator must be falsy. Python doesn't operate that way, and Python has actually explicitly documented the fact that it does not operate that way. There is no relationship between any of the comparison methods. So in fact, the bug here is an error of omission. We need to define a Dunder NE method anytime we define a Dunder EQ method. And I think this is sort of the way most people end up getting into the Dunder rich comparison methods in the first place. You have some sort of model thing, you do the equivalence comparison, which defaults to identity, and since Aristotle, the instance of one Aristotle and the instance of another Aristotle are not equivalent, you end up first saying, Aristotle.id equals Aristotle.id, and then eventually you get tired of writing that, and you discover this. So you'll be just fine with equivalence, as long as you define non-equivalence. And again, we make sure that we want to return not implemented. Once we add that, we actually get the desired value, which is, sorry, having technical difficulties.
Yeah, sorry.
Cool. So this is actually correct. So now we've done equivalence. And this is where we sort of go really hardcore philosophy nerd. In my brain, a lot of times when you're a philosophy undergrad, you spend a lot of time having really important discussions, like who is better, Aristotle or Kant? Solving the real problems. In my brain, this always sort of shook out to be this Street Fighter start screen. You're going to have a battle royale. It's not like that in reality, but this is sort of the way my brain thinks about it. So we want to actually do more than just compare for equivalence and non-equivalence. So we're going to go one deeper. We're going to define a greater than method, Dunder GT. And then we're going to compare the reputations of the philosophers, because that's ultimately what philosophy is all about. So again, here we do some is-instance dancing to make sure that we can actually compare them. We don't get an attribute error. And then if self and other are not of the same type, we return not implemented, which says, we're not going to compare against this. And then we can actually have a battle royale between Aristotle and Kant. So Aristotle's reputation is 10. That is a fact. Kant's reputation is 8. Also a fact. Aristotle is greater than Kant is true. No. So, Kant is less than Aristotle is also true. This actually is correct as well. What's confusing about this is that we just learned that there are no relationships between comparison operators. We just have this really weird problem where EQ, because NE wasn't defined, when we called not equals, we weren't calling and returning the Boolean false value of the return of equals. So this seems incongruent. But again, and this is really kind of more talk about how much of my life has been wasted by not reading documentation first. If we go in and we look, what happens here is actually not that we're returning the Boolean false of greater than when we use less than. What happens is that methods in Python end up being what's called reflected. So greater than is the reflection of less than, greater than or equal to is the reflection of less than or equal to, EQ and NE are both their own reflection. And so what that means, if we take a look at this, we're going to add some, Hillary Mason will be quite upset with me for debugging with print statements, but here's a print statement. And what actually happens is that Aristotle's greater than method is actually called both times. So the reason that's happening is because Kant does not actually implement the less than method. But Python says, well, let's look at the right side and let's look at the reflected method of less than. Oh, Aristotle has the reflected method of less than, which is greater than. And so this is still true because Python knows what to do. It knows it can do the right thing. So again, this is actually congruent because it has nothing to do with the relationship and everything to do with the reflected behavior of overwritten operators in Python. So actually, I presented this deck to my CEO, who is technical, which is awesome. I would highly recommend that all of you work for a technical CEO at some point. It's a rare but beautiful experience. And he was like, well, you should be raising not implemented, because Python has a not implemented error, which you raise, which is what you do with errors. Not implemented here is actually a constant, and it is a constant that has a special value. It's a singleton constant. It has a special value that when you return it, the Python interpreter says the method basically exists, but is deferring to Python to figure out what to do. Typically, you do this if you're comparing against the type you don't understand, or if you want to explicitly say, I'm not going to implement this. String uses this. So if you were to call string on dunder string's explicit dunder LT method on an integer, string would return not implemented. And it would happen for a floating point, it would happen for pretty much any type that string does not know how to deal with. The other pattern here is sort of the way set does it. What set does anytime you throw something set doesn't understand is to throw the type error. It's really sort of a tomato kind of thing. So, this slide is very complicated. I guess the point of all of this is that there is actually a fairly well-defined way in which the Python interpreter will choose which method is called. And if you just understand sort of what's going on, you can actually figure it out deterministically, as Python does. It just happens to be a little more complex than it probably looks at face value. Like when you were trying, remember we sort of got into this mess because we wanted to compare Aristotle and Kant for equivalence based on their IDs. And now we're at a point where we look at the left side, and if the left side method, when we try to access it, doesn't exist, Python will say we'll try the right side reflection. If it does exist, it will try the left side. If the left side returns not implemented, it will try the right side reflection. If the right side reflection returns not implemented, it will turn to the default, or if the right side reflection method does not exist, it will return the default comparison value, which ends up being equivalence. Or sorry, not equivalence, identity. So it'll compare the intern value, or the ID, of that object. And if the left side method exists, we return, and doesn't return not implemented, we return as expected. I bet you thought that was all we're going to do in the philosophy nerd game. For those of you, I can show of hands, who knows who Foucault is? Yeah, Yes, nerds. Awesome. So Foucault is a postmodernist, and they always ruin everything. So let's see what happens when we introduce postmodernism into our equation. So postmodernists are not really philosophers, but they do inherit philosophy. I'm sorry to any postmodernists who think you are philosophers, you're not. And so we define this less than method just because postmodernists are contrarian. So we have a greater than method on philosophers, and postmodernists implements less than, but not greater than. And because Foucault is a big believer in the panopticon and authority, Foucault doesn't care who he's compared against, he is always greater than them. Or in this case, never less than them. Unless it's not a philosopher, in which case Foucault doesn't know what to do, so he returns non-implemented. So, Foucault's reputation is a 6, again, that's a fact. Aristotle's reputation is a 10. When we compare Aristotle to Foucault, we should get a truthy value because Aristotle's reputation is greater than Foucault's, and because Aristotle is on the left-hand side of the comparison, so that's the side of the comparison that should be preferred because it would not return non-implemented because Foucault is also an instance of a philosopher. Oh, you all saw that coming, right? Anyway, so what's actually going on, let's go back to our debugging by print statement, is that Foucault's less than is getting called, even though we're using the greater than operator on Aristotle on the left-hand side. Just give you a second to process that. What's actually going on here is that if either side inherits directly from the type of the other side, so in this case, the type of Foucault is postmodernist, the type of Aristotle is philosopher, postmodernist inherits philosopher. Strictly speaking, it's if the type of either side is in the MRO, the method resolution order of the other side. Python will say that side is more specific than the other side, so we should try that side's operator first. And so Python says, oh, so Foucault has the reflected method of greater than, which is less than. And Foucault is more specific version of a philosopher than Aristotle. So I'm going to use Foucault's method, and it returns false. This is actually a very good case for never doing this. Like this case should never come up in your code if your code is well designed. You should have some sort of philosopher mix-in. Nothing should ever be directly a philosopher type. And then all the different kinds of philosophers should mix in that philosopher type. And then you can compare, say, Aristotle, who you would call a philosopher, who would inherit from some sort of philosophy mix-in, versus Foucault, who would be a postmodernist, who would inherit from the same philosophy mix-in. And this would work as expected, because each one is a type that doesn't inherit directly from the other, but they both share a common root of inheritance. And in that case, Aristotle would actually work correctly. The point of all this funness is that this is very, very complicated. What we started doing was we started to compare the left side and the right side IDs for equivalence, and then we had a bug, so we defined the not equals method, and then we started to compare the reputations of philosophers against each other, and so we defined all of these other methods. And at the end of this, what we have is this really, big flowchart that is actually even less complicated than reality. And so the point here is just that as you start to go down this road, just realize that you're taking on a tremendous amount of complexity, and make sure that you actually test all the things. That ends up being kind of difficult. The reason it ends up being kind of difficult is because every single time that you want to test, less than, that the dunder less than method is functioning properly, you need to test the dunder less than on the left side. You need to test the dunder less than when it's used with the greater than operator and that object is on the right side. And you need to test basically a whole bunch of other cases that have to do with this sort of inheritance. To do sort of metaprogramming around that, to avoid lots of functions that are like 4 lines and iterate through all those particular cases explicitly, the operator module is actually fantastic. So the operator module implements LT, GT, dunder LT, dunder GT. On top of that, it implements all of the bitwise operators. So there's bit and, bit or. On top of that, it implements all the arithmetic operators, so you can do and then all of the other dunder stuff. So anything that's in the document object model, there is a method that allows you to program functionally against that operator in the operator module, and that supports various kinds of metaprogramming that you wouldn't be able to do without really, really sort of nasty eval type stuff. So I would recommend that. So the next sort of gnarly thing here is these are all of the actual comparison methods that are supported. They're all, again, on the same page, documentation. There are lots of methods, and they all end up looking exactly sort of like the methods we've already defined, right? Type check it, check for the existence of an attribute, and then once you go beyond that, just sort of, actually do the thing or return not implemented. Again, once you read the documentation, you will find that the standard library actually has support for this that is really quite nice. So in the functools module, there is a decorator called total ordering, and you use total ordering to decorate classes. And total ordering requires that one of the comparison operators be defined. By convention, it's usually LT, though here I use GT. And typically requires you to have an EQ defined as well. One sort of gotcha with total ordering is that total ordering does not actually reflect EQ for any. You also have to define an any, or else we're back at the beginning of the presentation, and we have sort of violated the law of non-contradiction again. So if you use this, you will end up drastically sort of cutting down on the code that you end up writing. So, you might sort of be asking yourself at this point, like, there is so much duplication of code here, and the default behavior is so against what sort of like you would expect if you were just going in to do what we wanted to for equivalence. Why in the hell does Python not just say, you just define an EQ and then you get the NE for free and it's the Boolean reflection, and you just define an LT or a GT and it does the reflection, and you just define a GE or an LE and it does anything it wants. And if we were to go back to the documentation for this, what you would find is that you would find that actually none of the values that are passed to any of the comparison methods and none of the values that are passed back to the comparison methods are ever coerced, right? So they're always exactly what they are. This actually differs from methods like contains. So if you use dunder contains to override an in-operator Python, it will actually coerce the return value to a Boolean. So it calls bool on it and uses the dunder bool method to do that. Anything that's passed back from dunder bool is also obviously coerced to a bool. But that is actually not the case with the rich comparison methods. So I'm not necessarily going to recommend that you do this. But after, so I used Django for a very long time, as I'm sure many of you have done and still do, and then sort of switched to Flask about maybe 2 years ago. And when we switched to Flask, we also switched to SQL Alchemy. And for those of you who are going to be here tomorrow, there's going to be an awesome, very long talk by the author of SQL Alchemy that I highly recommend you all check out, because SQL Alchemy is awesome. That's an endorsement. But SQL Alchemy sort of has this kind of cool filter methodology that is really nice and like a breath of fresh air when you're coming from Django, where you have like name dunder in equals as a keyword argument. You're kind of like, this is sort of horrible, but it works. And what it does is it basically allows you to just say, model.column double equals value, and that just works. And that filters your query and does so in a very lazy way. And that sort of got me thinking. It's good because this talk's going to end up being short, actually. So all of the interruptions that you want are great. I need to pad this thing. So what it's actually doing there is something similar to this. So I have an object, I have class X that I then instantiate to the singleton X. I chose X because we all name our variables super well, so this should never collide with any variable in your code. I'm being polite. And so at the top, if you look at, we've got an EQ, and the EQ doesn't return a Boolean value. The EQ returns a lambda. And all that lambda does is says, take an argument that's passed in, and then compare it against other that's passed into the equivalence operator. And then I just go through sort of all of these methods and define a lambda that implements that function. Now, I could have sort of made this a little ugly and meta-programmed this out with the operator module, but I think this is actually pretty clean. And then the way that you end up using X is you can say filter X double equals 2, and I can filter out a range of 5. There's some missing parentheses there. I apologize for that. And then you can say filter X is greater than 1 against a range of 5. And so what that's doing is X double equal to 2 ends up returning a lambda. That lambda implements, as you iterate over filter, the values of the range are passed into it as X. 2 is the other. Okay, so 2 is other up here. And so we just say 0 equal 2, no, 1 equal 2, no, 2 equal 2, yes. And so we filter to just 2. And then we do the same thing for the greater than operator. And personally, like, I wouldn't highly recommend doing this all the time, but I find this to be much more attractive and idiomatically correct than the lambda syntax that we have in Python. And this is sort of, anyone who's using SQL Alchemy is already familiar with this sort of style of manipulation. That being said, yeah, there's a project I wrote called HappyPath, where I took that to the extreme. It was for generating like lots and lots of text vectors. Having other people had to live with it for a while, not myself, because I don't actually use it. I'm a manager, so I'm not doing that. But the people who have lived with it, I think this is the cautionary tale. You don't necessarily want to be doing things like this unless you have a really, really good case. So like, while this is very, very expressive, I would never do this with filter in reality. Just because someone's going to look at it and be very, very confused, because there is no call there. So, like we know, what did we learn? So we learned that comparison methods are extremely well documented, and the first thing you should do when you encounter something in code that you don't understand is to go to the documentation. We also learned that there is a fairly robust, although slightly complicated, methodology for choosing which comparison method is used on the right and left side. We learned that because this is complex, you should test this, and that the operator module is a very good way to do that. And we also learned that because comparison methods are not required to return Boolean values, you can do lots and lots of crazy stuff with them. And I'm very short on time. I apologize for that, but thank you very much. And we have plenty of time for questions.
Ask you a philosophical question.
Okay.
How do you think the implementers of Python could have done this better? Maybe how other languages do it better?
Sure. So the question is, how do we think Python could have done this better? I actually think it's pretty good, all in. You know, this is actually not the first implementation of this in Python. This particular comparison overriding was implemented in 2.1, or introduced in 2.1. Before that, you had Dunder CMP. And Dunder CMP sort of functions more the way you would expect coming from other languages, which is it returns like, you know, -1 or 1 or 0 to determine its position, or returns sort of relative values when you compare against, which is good for sorting operations, but it doesn't allow these sorts of styles of metaprogramming. Yeah, I think generally speaking, it's actually a pretty good implementation. It just tends to be quite verbose. But total ordering actually solves that problem pretty well. Yeah.
Is there a performance hit for using total ordering versus explicitly writing the comparators?
I think there is only, so if you look at the source code for total ordering, what it's doing is it has a dictionary of lambdas, and it's taking a class and then it's assigning lambdas to all of the Dunder methods that aren't there onto the class. It's pretty negligible, but yeah, I would definitely recommend using it whenever you know you're returning Boolean values, because it just cuts down on, you know, rewriting the same 4 or 5 lines of code over and over and over again, like 8 times. It's pretty low.
2 questions.
Sure.
One is that I looked at those slides and I saw these unexpected results, and I didn't completely rock or whatever understand.
Sure.
And I'm wondering, what's the likelihood as I get into Python that I'm going to encounter these unexpected results? Is that only if you're in a certain situation, or? Well,
now that you've seen this talk, 0, I think, if I've done my job. I think, so if we want to go back to like this guy, this first one, yeah, this is the way to do it. Cool. Look at that. So like this, actually all of the unexpected behavior in this presentation is stuff that I've actually encountered in the last 6 years. There are ways to get around this. The way to get around this is to not write your own ORM. So that would be the way to not have this problem. Is the company I was at, when I encountered this problem, we had an ORM-ish thing that wrapped all of our SQL that we had written ourselves. So they had done it before I was there. And we weren't using sort of any sort of ORM. So we were using a thing called WebWare for Python, which I doubt any of you have encountered, but for those of you who have, you understand how bad that is. If you're using like Django, you would get around all this stuff because Django is actually doing all the right things with the comparison operators. That being said, like you are going to at some point want to implement EQ in particular is probably the one you're going to want to use first. And when you do that, I would say more times than not in code review, when I've seen someone doing that the first time, they forget to define any, which is usually fine. Any, yeah, it's all right.
Yeah.
They forget to define the reflection method here, right? That happens all the time. Like I would say that's actually probably the normal case. And I don't even think it's necessarily a documentation issue. I think it's like, I know that things override this thing. I want to do that. You go to Python, you find the method that does that. You in the docs, you implement it, and you're done, right? And then at some point, someone is going to call not equal on that thing, and that's a ticking time bomb, and you're going to run into that. So I would say this one you're going to hit all the time. I think that the greater than, less than stuff is not implemented nearly as much. Like I think really for the most part with your custom objects, you're going to end up implementing the first two. This stuff it's very infrequent that you would see someone actually go through and implement these unless you were implementing some sort of numeric type wrapper or, set is a good demonstration of the power of these sorts of operators against, iterable types. But you're going to run into these a lot less.
So my second question, if you're willing to field it, I'm curious why you switched from Django to class. And you already happy with yours?
Oh God, are there any Django contributors here? I will say that my preference, and there are actually other people in the room who were there for that particular choice. I will say that over the last 4 to 5 years, I've seen a pretty big shift, and I personally have gone through a pretty big shift from sort of this MVC on the back end to an MVC on the front end and a very small set of services on the back end. You typically REST or sometimes JSON RPC. And I found we were going through the process of trying to build out that set of APIs on the back end. And we actually started doing it in Django. And I think what we found in Django was that Django is very good when you're doing all of the parts. But for a very small API, the problem we encountered was that there was just a lot of stuff in Django that we weren't using, and that Django got we ended up sort of feeling like we were working against the framework a little bit. We still use the ORMs, but like the forms were gone. We didn't need the templates. Like we actually were using Jinja templates anyway in Django. And like the URL routing was not as nice as we wanted, so we started using Workzoid inside of Django. And we kind of realized we're using Flask, basically, because that's Flask. If you had an application object in, you've got Flask, that's the whole thing. It's just those two packages and an application object and some session state. Workzoid and Jinja. And so what we ended up at was kind of this decision where it was like, we want something that's very, very small and does very little for us, so that it doesn't get in our way. And that's kind of how I made the switch to Flask personally. I think a lot of people feel that way. I think a lot of people also have had great success with Django and like TastyPie or other or Django REST framework, doing very similar things, which are sort of frameworks that take all those top layers and make Django a much more suited, sort of framework for doing API development with. But for me at the time, in the place, I think Flask was the right choice. And I'll say, having changed jobs now, we're also going to be doing we're going to be moving to Flask at that handshake as well. Just because it's just a very nice framework. Can't say enough nice things about Flask. I think it's awesome. Cool.
So what you have presented here is a fairly complicated system, and I guess the advantage of that is that it allows you extra degrees of freedom in the behavior of the object.
Yep.
I'm wondering what you think is the motivation behind it and what we as developers can use it, how we as developers can use it to our advantage.
Sure. So I guess the question for anyone who didn't hear and for the video is sort of, if this framework is very complicated, what are the advantages and how can we use it to our advantage? And I guess what is the impulse from a design perspective?
Right.
I mean, I'm not the author, so I couldn't comment on exactly why they designed it this way. I think the principal design impulse is CMP is not, the original CMP implementation is not robust enough. Let's find a more robust implementation. I think also when you start to look at the kinds of operations that would be supported, especially in collection types, if you didn't have to return a truthy value, I think it actually opens up quite a bit of flexibility. And so what I would say is like the functools total ordering stuff will make it nearly as simple as if you just had CMP anyway. So you have that in the standard library. I think the place I find myself using like this level of firepower the most is with interval types. So like you could take, I guess someone posted a question on the Python subreddit the other day, which basically said, you know, I want to be able to have my comparison operators for sets return subsets, as opposed to what it does, which is basically check for the existence of a subset or a greater than set or a superset or whatever, and then return the pool value of that. And the answer is actually quite simple. Like you can take, you know, frozen set or immutable set or the set primitive like capital set, and then you can just override a couple different attributes, and then you can build these really sort of very expressive things that return values that if you were to evaluate them to pools would also make sense, but are also iterable, so if you ever wanted to use them in that capacity, it would also make sense. So I think iterable types are probably the best place to use them. I also think anytime you're doing like lazy loaded filtering, which is like exactly what SQL Alchemy is doing with it, it's also pretty fantastic. It looks a little different than this like lambda layout, but like basically you would have some sort of like filter, lazy filter object, and then you would just manipulate state on that object and return it. And then you would just keep mixing in these lazy filter objects into your actual query so that when you iterated it the first time, the query would be constructed the right way. So I think any sort of lazy evaluation iterable is also pretty well suited to this. Having said that, I think you want to do exactly what SQL Alchemy does, which is like SQL Alchemy has a function or a method for every single operator that it supports. So there's like .eq, there's .is underscore, there are all these functions, and I think if you're going to provide that interface, you should always provide a functional interface as well. Because as cool as like that is, and as expressive as that is, when you start doing more complex things with that, you end up with a lot of parentheses, right? Because you have to group all the expressions, and then you're like, oh, well, I'm using all these other methods. I'm going to implement the bitwise operator, and now I'm going to say x double equals to bitwise x greater than 1. And bitwise has higher precedence than logical operators, and now you have to do parenthetical groupings and all this stuff. So just be careful about that.
Just small note that you'll have to be aware if an object has these kind of operators implemented, because when you're doing just implicit test for none, this might evaluate actually to another object, therefore it will be kind of true. So you have to test explicitly if an object is none.
Yeah.
So if you know that you can get this kind of object, always test if object is none instead of just if object. Because if you just do if object, that evaluates to some kind of object another, which is object that is not none. Example is SQL Alchemy. If you have a variable called, for example, table, and you test if you have that table or not, you just write like if table, it always evaluates true. But you have to write if table is none to get the result you actually expect.
Cool. Anyone who wants to bounce, by the way, welcome to, but I'll keep taking questions until we run out of time.
I was wondering, are there any other instances where, or any other time when it's Python return not implemented other than done methods? Like in methods maybe that we're defining ourselves, or something like that?
So, I mean, I'll bring it back. I have the whole documentation for grading my presentation, so we can actually look at it. I think there are some other cases that are in that ellipses there, but basically not implemented constant has a very specific meaning in Python, and if the interpreter ever gets it, it's going to do things automatically for you based on the assumption that you're using it correctly. I would say, like, if you're not going to implement a method in like a base class, I would always raise not implemented error. That's more idiomatically correct, and it's like sort of the expected behavior. This I would only use in the cases where Python explicitly says, like, use this constant. I actually personally don't particularly like that it returns this. I think it's kind of weird and not what's expected. But yeah, I would only use it in the cases where it's documented, and in all other cases I would break it out.
Sorry for the sidetracks. But you mentioned this project that you had, HappyPath or something,
Yes, HappyPath.
that have used these and like,
Yes.
yeah. Can you remind me of giving us the elevator pitch?
The idea of HappyPath was that test cases with complex form sets that had interdependent requirements on one field against another field. Like for instance, if you choose the U.S., there are 50 valid state options, and all of the state options are invalid. That's one example. Be generated could actually is of walk, efficiently expressed sort of. Digraphs are really not fun to like implement by hand, so like they're very verbose. So like any you might get by using your act would be negated by how ugly the digraph code was. Even with like there are some rules in Python, but it's like if you're defining nodes for everything, it's not very nice. It's like well, what if I have to do in the tree next based on complex rules. Those rules being defined by comparison operators, but then you can join those rules with bitwise operators. So I can AND those rules, or those rules, and XOR those rules. Oh, also there's unary not. I think the mistake in that project, and it was a good project for me as a learning experience for Python, but it was one of those projects where it's like, oh, and I could do that, and I could do that. And it's like all of a sudden unary not was like, it just got kind of gnarly. When you first discovered the documentation about all of the magical stuff that you can do with operators in Python, go do all of them in a project. Don't open source it. Don't make your coworkers use it. And then use all the lessons you learned at the appropriate time later, which is probably not that time. But it's actually, the idea is fantastic, and I'm sure that I would love for someone to implement that. So if anyone has any spare time, like a very nice grammar for generating, paths, vectors through test cases in complex form sets would be awesome. I failed pretty miserably at trying to keep it simple myself. So if you can do it, more power to you. Would like to contribute to it. Awesome. Thanks, guys.